In this series of lectures we'll look at the PIX firewall, and then we'll move on to the ASA firewall and some of the main techniques involved in CCSP. Basically, the PIX is a multi-functional device. It has basic firewall rules in which we can set up ACLs, and we can also filter it at a high level, such as with URL filtering. We can also block ports and enable network services. A key advantage is that the PIX firewall actually understands how certain protocols work and can open up ports automatically. It does intrusion detection systems, especially with the IP audit command, to be able to detect more advanced intrusions than many firewalls can. It does shunning, where we can shun an intrusion along with detecting it. It supports VPN access, especially with the IPsec protocol and for tunneling techniques such as PPTP. It does cut-through proxy. Cut-through proxy allows a single user authentication or service authentication through a proxy, and then the user is then authenticated to use that service. And as firewalls are so important, it allows failover devices. The most basic PIX that we have is called the Small Office or PIX 501. It is a relatively small processor, runs at 133 MHz with a small amount of memory, and can support up to 7,500 connections. It only has one external connection and one internal. The level above this is the PIX 506E. It has a faster processor, more memory, and can support an output rate, a throughput of about 20 megabits per second with about 25,000 lines. In this case we can see we have Ethernet 0, which is outside, and Ethernet 1, which is inside. So this is untrusted and this is trusted. We have the console port here, in which we can connect a terminal to be able to configure it. There's no failover at all, and it only has two connections, as we can see. The first medium-sized office device is the PIX 515. It has a much faster processor and supports more memory. Overall, it can support 130,000 connections at any one time and can give a throughput of 188 megabits per second. So we can see here that we have our Ethernet ports as default, and then we can have additional Ethernet ports which can define our DMZs or extra connections. Again, we have our console connection. Basically, the throughput typically depends on the encryption that we use. 3DES only gives us 22 megabits per second, where AES encryption gives us 63, although we can accelerate that with a VPN accelerator. There's also a VPN, there is also failover cable support, and as we can see here we have a PCI connector, interface adapter, to allow us to expand the number of ports that we actually have for fast Ethernet or for gigabit Ethernet. In this case we can see there are 4 additional Ethernet ports. There's 2 licenses that we can get. We can get a restricted license or unrestricted. With unrestricted we can support an integrated accelerator, failover, more LAN support, and VPN acceleration. The level above is the PIX 525, where we have again a faster processor. We have more scope for extra connections apart from our 2 Ethernet 0 and Ethernet 1, and we can have up to 280,000 connections at a time. The thing about a PIX is that a PIX tries to remember all the connections and the state that they're in, so each of these connections takes up some amount of memory, in the actual device. Overall, it can support up to 8 connections. For much more robust systems, we have the PIX535, a 1 gigahertz processor with 1 gigabytes of RAM, and can support up to 500,000 connections with 10 network interfaces. The SA device is now one of the new devices. It has a Pentium 4 architecture, 2 gigahertz processor, and up to 0.5 gig RAM. It supports PIX7 and PIX8, as we'll see, with 8 interfaces, integrated VPN, and integrated SSL VPN. The basic throughput is about 450 megabits per second, but that obviously reduces with 3DES. And we can have over 280,000 connections at any given time with 750 VPN peers. The costs are typically such as this. Top of the range will go up to $10,000 or about $20,000. So what does the PIX firewall look like? Well, basically it tries to simplify security in that we have untrusted, trusted, or DMZ. So we have 3 main connections that we typically have. Basically, nothing is trusted from outside to go to the DMZ. Nothing is trusted from the DMZ into the inside zone. Each port is given a security level. Typically this is defined as 100. This could be a security level 50, and then this could be 0. Traffic is not allowed to flow from a lower level security priority into a higher one. So we can see here traffic would be allowed from here to here and from here to here, but not any of the, and also from here to here, but not any of the other directions. For this to happen, we create a route into the network. As an example here, we might have our outside port at 0.2, and here is our main gateway. We have our DMZ, and we have Ethernet 2 is typically here. E0 is typically the outside. E1 is then inside, and then E2 is in our DMZ. So you can see here we have our web server, forward-facing web server in the DMZ. Typically the PIX uses network address translation. So what we define is what's called a global pool. The global pool will remap the local address into a global address. So in this case, 172.16.0.2 will be seen from the outside with one of these addresses. Same with this port here. This port from the outside can be accessed from one of these addresses within the pool. So for example, this address here from outside might be 192.168.0.20, and the web server here might be 192.168.0.21. Okay, so what does the PIX firewall look like? What we're going to do is that we're going to define that the top screen is PIX 6.0 and the bottom screen is PIX 7 and PIX 8. Some of the certification questions still relate to PIX 6, so we'll cover both. The basic PIX that we have is E0, E1 is inside, and then INF2 is E2. For newer versions of PIX, we actually need to define these names before we actually use them, but in previous versions these were already defined for us. PIX 6 is a fairly flat structure. With PIX, each interface has a name, inside, outside, and INF2. This allows us to create clear documentation for the interfaces. In PIX 6 we had a fairly flat structure where most of the configuration was done within the config, where in PIX 7 we have a more hierarchical structure that is normal in Cisco IOS. So in PIX 6, to set the IP address of the outside interface, which is this one here, we say IP address outside and then give the IP address. Interface E0 auto enables the interface. Here we do the same. Interface 0, set the IP address. It shouldn't be there. And then do a no shutdown in the port. So this is their most basic configuration. So here we see when we're setting the other interfaces, we use the INF2 and the inside to set, and then we enable the second ports. In this case, if we just remove that, we have E2 and E1. We do a no shutdown. The key thing is that we need to give them a name. In this case, E1 should actually be inside, and these are giving our IP addresses. We must always do a no shutdown to enable the ports. So we can set the name in PIC6 with nameif, and then we define the port, the name, and the security level. This is a security level of 100 here. This has a security level of 50, and this of 0. In the PIC7 ASA, we can define the name with nameif, the security level of E0 is 0, and we do a no shutdown. Same again, E1 also is configured this way. For shutting down the ports with PIC6, we see the auto and then shut after it, where we can use the shut command to actually shut down the ports in PIC7 ASA. To generate RSA keys, the command, and we need to generate RSA keys if we're using a VPN or IPsec. With this, we say CA generate RSA key, and that's 256-bit keys. Before we do this, we must set the domain name of the device, and we typically set a user. So for PIC's routes, these are an important element, as these will be used to define the default gateway and also to allow the connections between the outside and the DMZ, and also from the DMZ back into the inside. It is these two routes that do not exist by default. So in this case, we see route outside 10.0.0. That matches this part, should be sent to this address. So this says that any default traffic that we have gets sent off to the address 206.59.124.10. This will be a default route. We can set the banners and the domain name and so on. The show route will allow us to show the routes that we have. So the table that we have a routing table, and here we can see if we set the IP addresses of our PICs. So this sets our inside address, this will set our outside address, and then this will set our DMZ. Once we do a show route, we can see that we have 3 static routes set up. Anything with 10.1 in it will be sent to 10.1.1.1. So we can see here that anything that say arrives on this port will be sent automatically to this port. The inside is another static route, and then the DMZ. Same will go for our PICs. So we can see here that that these 3 static routes are set up when we configure the 3 ports. Then we must configure another static route. In this case, anything from inside that is destined for this network, which is this network over here, will be sent to this address. So you can see here that anything that comes in with this part in the address, so it comes in here, will be sent automatically to this port here. This port here will know that that route exists on its device and will send it to this network. So we can see here that we must force the PICs to do certain routes. And we see here we have 3 static and then 1 other route which isn't actually connected to our device. Then we can set the default gateway. So this says any other address that we hear, send the data traffic to this port here. It will then be up to this port to be able to send it out, hopefully onto the internet. We must force the PICs ASA device to do these additional routes, and that they're not done by default. So any packet that might be here for any address that isn't in this network, the PICs will pick it up and then send it to the default gateway. A key service on the PICs is called Fixup, and with Fixup, the PICs tries to fix certain protocols. For example, if we use FTP, FTP typically has a negotiation for the ports it uses, and a server port is set up on the client. This means that for a normal firewall, this port might be blocked, but the PICs understands this negotiation and fixes up the firewall so that the connection is allowed in as long as the client on our trusted network has initiated it. So typical Fixup protocols are FTP on port 21, H323 is our video conferencing specification, HTTP, RSH, RTSP, SIP, Skinny, SMTP, and SQL. SQL StarNet typically requires a negotiation for the port. These are typically defined by default, but if we have to redefine the port in which they operate, then we can redefine the Fixup to be HTTP port 161, FTP port 60, and SMTP port 84. The device itself normally works on network address translation, and here we see an example. So we're setting the name here to be DMZ. Next we define this port address. After this we define the inside address and then the DMZ port address. After this we define that we have an inside network of 192.168.1.1 behind here, and in the DMZ we have 172.16.0 network from here. Now what we do is that we map these two private addresses into a global address space. So on the outside, map 1, which is this one here, into a range 10.1.1.2 to 1.200. So then this will map the addresses here into this address space. So for example, this port from outside might be accessed if it's the first one to get an address with 1.1.2. Another address here might be 1.1.1.3 and so on from outside, depending on how they're allocated. The second set will now be allocated from 201 to 254, so the addresses from here will be addressed through these addresses. So for example, 172.16.1 might be accessible from outside with 10.1.1.201. With NAT, we can we typically define NAT on a higher level interface and global on the lower interface. So global is what's seen outside, and then that translates into a NAT. So these are the addresses inside our network, and these are the addresses that are accessible from outside. No traffic is allowed through the PICs unless it goes through a NAT translation or is a static mapping. Typically, the hosts in the DMZ might be available through a static mapping because we want them to be have a fixed IP address rather than from a pool. So along with NAT, we can have port address translation. Port address translation is useful because we typically can use just one address and we overload it with multiple TCP ports. So from outside we have one address, but that can connect to multiple addresses within inside the network. So in this case, we can define our outside address here, our inside address here, and then our DMZ here. And then we define our internal address pool of 192.168.1.0 or 1.x, our DMZ pool as 172.16.0.0, and then to enable port address translation we just say outside one interface for both, and we will get port address translation. So then this will use one address on the outside for our whole network. And we can see here's another example. On the DMZ we allocate a local pool. If we don't want these addresses to be NATed, we have a 0 in the DMZ, which means there will be no network address translation. A key concept is for static mapping, and with static mapping we map an outside route into an inside one. So by default, as we've seen, then we get no traffic from here to here, and there will be no traffic from here to here. What we must do is set up a static route that will allow traffic to flow in these two directions. So in this case we define our IP addresses. Next we say, and we read it like this, that the outside node will be seen as 10.1.1.201, and the inside and the node in the DMZ is 172.16.2. So this means that this address will be the address that is used outside to access this server with inside the DMZ. Again, outside relates to this node, inside relates to this node. So this node here will be seen from outside with this address. So if someone wanted to access this machine from outside, they use 10.1.1.202. In this way we've created a static mapping. We typically do this for nodes within inside the DMZ. Another example here shows us that we can set up one to be from NAT. In this case here is the mapping, and then we can also set up a static mapping so that this node here is seen from outside with this address. We can use access lists with inside the PICs, which is a fairly new feature for the PICs. And in this case, again, we can set up our IP addresses. We set up our static mapping, so then this node here, which is this one, is seen from outside with this address. Next, we can define an access list, and this is permit any traffic to this address using telnet. So we can see here we're using the external address, so when we apply the access list, which is here on the incoming direction, we use the address which it is globally seen as. So this will allow telnet access to this node. Then we can say we allow web access to it, and then we can deny all other traffic. So this will stop all other protocols apart from telnet and web access to this node here. Then we can apply it onto our outside interface for the incoming direction. On the PIC7 and ASA, we can use a more structured approach. In this example, we say that we permit this host access to this host. So this is 10.1.200, access to 10.1.201. 201 is this device here, is the address of this device here, and we're allowing this host access to that host. No other host will be able to connect to this device through this port apart from 1.1.102. A key feature that we have in the PICS ASA is failover. The last thing we want is for a main firewall to fail, because it can cause the whole of the network to fail. So we typically have a backup device or a failover device in parallel with the firewall, which basically just watches the firewall to detect when it falls over. With failover, we typically either have an Ethernet connection, which is LAN based, or we can have a special cable called a failover cable that detects the traffic over the firewall. And typically we have the same PICS ASA type, same amount of RAM, same flash memory, same types and interfaces, same software version, and the same activation keys. We also need an unrestricted license and a failover license for the secondary. Unfortunately, restricted license cannot be used. So we have an activation key for this, and basically the two firewalls are connected in parallel. Most of the time the secondary firewall will not actually route any traffic, but will monitor the other firewall for its operation. Basically, hello messages are sent out every 3 to 15 seconds, 15 seconds by default, and if two of these hello messages are missing, then the secondary device will take over and will assume control. It will take over all the IP addresses, the MAC addresses, and if we have a failover cable, it actually knows all the connections, so there will be no difference in the connections that are occurring. So basically we can have power supply failures, we could have a primary reboot, interface problems, memory overflow, and so on can cause problems to our PICs. Basically the test that it does is it does a network interface test, so it just pings each of the ports to see if they're still alive, and then it will go into network activity and monitor for about 5 seconds. If it can detect network activity across the firewall, it will then cancel all the tests. Next, it will do an ARP test and request the last 10 IP addresses from the ARP table. Finally, it will do a ping test with a broadcast, and if all of these fail, then it will take over. For replication, we need to be able to copy the configuration from one firewall onto the next, and the write start by command is used to write standby. That should be standby command is used to write from the primary to the secondary. We can basically have what's called the stateful failover. The stateful failover, the failover cable automatically monitors all the connections that are going on with inside the primary and will replicate them in the secondary. The secondary then, these are ARP tables, the NAT tables, Fixup tables, routing information, IPsec, MAC addresses, hello messages, and so on, are all replicated on the secondary. The secondary will then inherit all the IP addresses and the MAC addresses of the primary, so users will not feel any different. The primary, though, will actually inherit all the IP addresses and secondary and MAC addresses of the secondary. In non-stateful, we basically just have a network connection between, and it will only keep the RAM configurations and session details. Unfortunately, we'll lose all the NAT translations and connections. So we can see here an example of the failover cable. So it plugs into the failover device, and we have our cable which connects to a standard 15-pin D-type connector. With LAN-based failover, we typically don't connect the Ethernet connection directly. We typically go via a dedicated hub or switch. We don't want to mix with other types of switch traffic. So this shows the failover with a cable. And for configuration, we say that failover is active, and then we define the failover addresses for each of our ports. So inside will be this one, INF2, and outside will be the secondary, will be the IP addresses that will be taken over on the device. For LAN-based, we can define our primary IP addresses. These are used to basically connect the device and should be unique. And then we define the failover IP addresses, which should be the IP addresses of the other device. Then we can define a key, shared key between the two, whether this unit is a primary or a secondary. In this case, this is the primary that we're configuring, and where the LAN interface actually is. In this case, it's INF2, and we enable LAN failover. Okay, so on the other device, we define a secondary, and we should automatically get the IP addresses when we write the configuration. So we can see here from the previous example, these will be the addresses that will be given to the other device, but the other device will take over these IP addresses in failover.